Okay, this is problem set 21, and this one is mostly on our Riemann sums and integrals, mostly definite integrals, I think. So yeah, just a reminder, antiderivatives and integrals are the same thing. We just call them different things sometimes, but it doesn't actually change anything. So let's go ahead and take a look at number 1. Looks like it's a question using Riemann sums. And it says that f of x equals 2 times sine of x plus 1 from 0 to pi. They want us to use a calculator to find these Riemann sums using a partition of 30 subintervals of equal length. And so I did go over this for one of the problems in my last video, in problem set 20, I think. But I will walk us through it again. Once again, I have a TI-84. I have not tested this with a TI-83. If you don't have a TI-84 calculator, there are plenty of TI-84 apps, both for phones and I think for like desktop computers as well, and probably for tablets as well if that's what you're using, though I don't know about that. But so basically, we first want to find that left sum, and let's just I'll just sketch this out a little bit to start off. So it's obviously going to be up to there, right? And we're going all the way to pi over 2, which means it's going to look something like this for that first bit there. It's going to look something, there we go. Something like that is what that's going to look like. And so we want a partition with 30 subintervals. Obviously, we're not going to write all of those out here. But let's first think about that left sum. Obviously, our left sum is different from our lower sum or underestimate because this is just all of our left points. So we're going to start with this 0 point, and then we're going to start with whatever comes next and kind of go like that the whole way through. But obviously, smaller distances between, right? So we're going to do everything up to exactly 1/30 before this pi, right? Because if it's our left sums, this part isn't going to get included. So let's go ahead and try typing it into our calculator. So once again, we're going to press that second button up at the top left of our calculator, and then go press that stat button so that we're selecting the kind of list part that's right above it. Then we're going to go and scroll over to the Math tab and select Sum, which for me is that 5th button there. And then, before doing anything else, we're going to go back. We're going to do second again, stat again, and this time we're going to go to this here, these operations. And again, it's that 5th one for me, and it is seek or sequence. We're going to select that, and then once we pull that up, we're going to have, on a TI-84, it's a little easier to see, we're going to have kind of a page that looks something like this. Let me just write it out. Okay. And what we know here, so this first part right up here is where we're going to type in our function. So in this case, it's 2 sine of x plus 1. So I'm going to go ahead and type that in my calculator, 2 sine of x plus 1. Then it asks for the variable. Our variable in this case is x. And our starting point, since we're doing that left sum first, it's going to be all the way at the left, so it's going to be 0. And our end point, like we said, is going to be exactly that 30th right before that pi there. So obviously, if we're going from 0 to pi, splitting that into 30 subintervals is going to mean intervals of this size, right? So we're going to stop exactly 1 pi over 30 in front of that pi. So pi minus pi over 30 is the same as 30 pi over 30 minus pi over 30, which is going to be 29 pi over 30. So that's what I'm going to type in to my calculator for my end. So 29 pi divided by 30. And then that step is like we just said, it's that pi divided by 30. And then we press paste and enter and have it run. And that's going to give us a left sum looking like this. Okay, now we want to do, probably easier to go ahead and do the right sum next. So once again, we're going to do all of these same steps, except now we're going to do that right sum. So our start point is going to be that point there, and we are going to come all the way to this pi. So instead of what we have here, our start is 0, our end is pi. Nope, our start is not 0, sorry. Our start is pi over 30, our end is pi, and our step is pi over 30. So remember, second stat, math, sum, second stat, ops, sequence. And then start is pi over 30, end is pi, same step. So that right sum looks something like this. And then we want to do that midpoint sum, which is just a little bit trickier, because that's going to be right in between here. So instead of a step of pi over 30, we're going to go right halfway between, no, we still have a step of pi over 30, sorry. Instead of a starting point of pi over 30, we're going to go right between that, which is going to be pi over 60. And our end point is also going to be right between, right in here, which is going to be whatever pi minus this is, which is then just 59 pi over 60. And then our step is that same thing because it's the same size interval, those 30 subintervals. And so that's how we're going to put it in this time for our midpoint sum. Okay, so second stat math sum, second stat ops sequence. Our start is pi over 60. Our end is 59 pi over 60. And our step is unchanged. And that gives us a sum of about this. And that's it. That's all they're looking for there. Number 2 asks us to approximate this integral by computing the lower sum and the upper sum for this partition here. So obviously our x cubed, if I was to sketch that out, it's going to look something like this, right? So I'm actually I'm going to sketch that a little bit bigger so we can get a clearer picture. So then we'll say that this is 8, 4, negative 4. So for that lower sum, of course, we want to underestimate, which in this case would be a, we want it to not cross over. No, we do want it to cross over like that because we want to underestimate. Sorry. So that's going to be this rectangle here. And then over here we want to underestimate, so that's going to stay 0, and then it's going to be this rectangle here. Okay. So our left, not our left sum, sorry, our lower sum is going to be, well, this is a distance of 4. Well, they're all a distance of 4, so we can factor that out. So 4 times this height is whatever negative 4 plugged into x cubed is going to be. So 4 cubed I know is 64, so it's going to be a negative 64. Then plus, we've got this one, which is just a height of 0, so it's 0, plus then this height, which is the height of 4, which is a positive 64. And these cancel out, so our lower sum actually equals 0. Interesting. Let's try that overestimate with our upper sum now. So instead of instead of staying under the curve like we just were, right, we're going to go over it. So this time I'm gonna, this part's gonna stay 0 because I don't want it crossing like that because that would go in the negatives. But here we're gonna have these. So our upper thing, again, factor out that 4. This is a 0 plus whatever this height is, which is 4 cubed, which is 64, plus this height now, which is 8 cubed, which is, I think, 512. Just going off memory. Then 64 plus 512 is 576. That's pretty big. So this is a very big difference in our over and underestimate here, and that's probably because it's such a small, or it's such wide intervals there, so subintervals there. So I'm just gonna, okay, and that equals 2304. So the actual integral is somewhere between these two. This is what we just found. Moving on down to our next problem, we want to approximate a different integral. This one is the absolute value of x plus 3 along these bounds by computing, same thing, so that lower and upper sum for a different subinterval now, or a different partition. So let's see. Obviously, an absolute value looks something like this. So I can actually, we can kind of rewrite that, and I would write that as a piecewise function, probably. So if it is x plus 3, then this gets to be negative when x is negative 3, so it looks, that's kind of how our absolute value here looks with its vertex at that negative 3 point. And we're going from negative 4 to negative 2, so this is the, this area under here is what we want to approximate. So probably the best way to do this, to try and like think about that integral, is we can, well, I guess if we're just using the sums, we can just do it that way. So that lower sum is going to be, oops, this is a little crooked, this is a little ugly. So that lower sum is going to look something like this, because we don't want to overestimate. Which, that just looks like it would be 0 though, because that vertex should be like that, right? Oh, because of those intervals, it's not, sorry, I misread my own question. Okay, let me redraw this a little bit bigger, a little bit clearer so we can see that. We don't even really need our y-axis in here. So we've got negative 2, negative 4, negative 3. And we've also got, in here, we've got that negative 3.5 and a negative 2.5 are part of our intervals here. So I'm gonna draw it like that. Now for that underestimate, like I said, that's going to be 0, that's going to be 0, and then it's going to be those rectangles there. So our lower sum is going to be 1/2, because that's that distance there, is that 0.5, times whatever this height is. So plug in a negative 2.5 in there, which is going to be the absolute value of 0.5, which is just 1/2, plus then on this side, which is, that's plug in that negative 3.5, plus 3 is a negative 1/2, but in the absolute value it turns into a 1/2. So it's also this, which is just 1/4 plus 1/4, or 1/2. So our lower estimate is 1/2 for those subintervals there. Let's try our overestimate now. So it's going to look more like this. So we've got a little more happening. So still got that 1/2, and we can actually factor out that first 1/2, which is the distance between them, right? And now that's going to be the absolute value of -4 plus 3, which is just 1. The absolute value of -3.5 plus 3, which is just 1/2. This one's also going to be 1/2. And this is also going to be 1. So now it's 1/2 times 3 3/2, or 1.5. Okay. Now they just ask us to compute this definite integral here. So remember, an integral is the same thing as our antiderivative. So I'm going to take a look at this, and I see that it really only is affected by our power rule. So I know going backwards from my x4th, it would have to be an x to the 5th, because we add 1 to that exponent, and then divide by that 5, right? But I've already got a 1/2 in front, so it's going to be 1/5 times 1/2 to the 5th, which is then 1/10 x to the 5th. And normally we would put that plus c, but when we're doing a definite integral, the plus c's end up canceling out, so we don't need to write those. So it's just 1/10 x to the 5th from 3 to -2. And the way that we then compute that is we plug in our upper bound into this, and then we subtract, and then we plug in our lower bound and subtract that, right? So if I plug in a 3, I'm going to get 1/10 times 3 to the 5th minus my lower bound, so it's going to be 1/10 -2 to the 5th. Okay, 3 to the 5th minus 3 to the 4th is 81. That times 3, 243. Okay, so it's going to be 243 over 10 minus, and actually it's going to be plus because this is going to stay negative, so those negatives cancel out. That's going to be 32 over 10, which is then 275 tenths, or just 27.5. Okay, this next one is a similar deal. So we've got pi over 2x, and of course pi is a constant, so it doesn't really affect our integral in any way. We just undo that power rule again. So this is an x to the 1st. Undoing that, I'm going to get x squared, and then that. So I'm going to have that pi over 2 times that new 1/2 there. So we get pi over 4x squared is our integral. And now we evaluate it. So it's going to be pi over 4 times 5 squared minus pi over 4 times -2 squared, which is going to be 25 pi over 4 minus 4 pi over 4, which is, well, I could just write 21 pi over 4, and that is our answer there. All right. Number 6, now they want us to set up the definite integral rather than just calculate it. So the curve that we're given, our function here is x minus 2, and it's bound by -1 to 6, and then they want us to compute that integral. So of course our bounds, we want to write that with our smaller bound, our lower bound at the bottom of our integral, and our higher bound at the top. If you write it the other way around, it's technically incorrect, but that's honestly an easy fix. If I do it this way, that's just going to be equal to the negative version of it flipped, right? So just careful with that. But we always want to do that lower bound at the bottom, upper bound at the top, otherwise the whole integral is negative. And it's just our function there, and then dx. And that dx disappears when we take that integral. So now, let's undo that power rule. So I know my x turns into a 1/2 x squared, and my -2 turns into a -2x. And then we've got to evaluate it. So I'm going to plug in that 6. It's going to be 36 over 2 minus 12. all minus, if I plug in that -1 now, I'm going to get 1/2 plus 2. So that's going to be 18 minus 12 minus 2.5, which is 6 minus 2.5, which is 3.5. So our answer is 3.5. Number 7 is another with our Riemann sums. And yeah, so we want to approximate this integral. So 2 cosine of x from 0 to pi using Riemann sums with the following partition. So, oops, didn't mean to do that. I would like those to go away. Okay. So, when we're dealing with trig functions, they're easy to sketch, so we might as well. So I know that from 0 to pi is going to be half of its period. That's the word. Okay. I don't know why I blanked so hard there. So I know it starts up here and goes down, and it's going to look about there. Something like that. Right? That's what our 2 cosine looks like. I didn't, it's going to be -2. Okay. So, using my left sum from along this bit here, I see that I've got a constant length of the subintervals, so I can actually factor that out. So my sum is going to be not 1/4, sorry, pi over 4 times each of these heights then. So my left sum is going to be this right here. Okay. So it's going to be this first height. So I just know that that's 2 because it's that plugging in the 0 there. And then plus this next height, which is 2 times cosine of pi over 4. Well, cosine of pi over 4 is square root of 2 over 2 times 2. Those cancel, and it's just square root of 2. Then, obviously, plugging in a pi over 2 gets us 0, and then plugging in 3 pi over 4, we're going to get a negative square root of 2. Because of our unit circle, it's going to be right over here, so our cosine is negative. It's a negative square root of 2 over 2. Obviously, times 2 cancel. So then these cancel, and we get 2 times pi over 4, which is just pi over 2. So our left sum is pi over 2. Let's try our right sum now. So our right sum is going to start with this rectangle here. Still have those subintervals of length pi over 4, so I'm going to factor that out. This height here we just determined was square root of 2. Using that right sum, so then this height is 0. And then this bit here, which we know is a height of that. And then you've got this. So I plug in a pi. I know it's a -1, so I'm going to get a -2. These cancel, so it's just -2 times pi over 4, which is negative pi over 2. And then our midpoint sums, a little different. So we're going to have rectangle here. I'm going to have that pi over 8. It goes right up. And this is the rectangle that forms now, because it goes right smack dab in the middle of these. Oops. And that's what that's going to look like. Again, it's that distance of pi over 4 still. Keep writing 1/4. Pi over 4. Now this is a little bit trickier just because those are not pretty numbers. But you know what? You know what I see? So if these were prettier numbers, then we would see pretty quickly what I see from this graph here. These are equal, but this one's negative, and these are equal, but this one's negative. So all of this cancels out, and that's just going to end up being 0. So that midpoint sum is 0. That's part of why drawing it out helps us so much. If you can do it all algebraically, I implore you to do so. But, you know, just visualizing things is helpful 90% of the time if we can do it. Let's try next. It says approximate using a right Riemann sum having 10 intervals of the same length. This integral here. So it goes up to 3 pi over 2 from pi over 2, and it is, once again, that 2 cosine of x. But this is on a different interval there, so we're going to get a slightly different answer probably. They just want to know what the right sum looks like, but we want to split it into 10 intervals of the same length. So honestly, I would go ahead and use our calculator for this. We can draw it out, but it's not fun to. So if you've already forgotten, you can rewind, or I'll just say it again here. So we go into our calculator, ideally a TI-84. I cannot attest to whether or not other calculators are able to do this, but we press that second button, and then stat, then math, then sum, then do it all again. So we do second, and then stat, and then ops, and then sequence. And remember, we first put in our function. So for this line, we want to put in 2 cosine of x. For our variable, we're going to put in x. Our starting point, this is a right sum, so we're not going to include that first pi over 2. But our end point, we know, will be that high point there. So we know our end point will be 3 pi over 2. The distance between 3 pi over 2 and pi over 2 is a distance of pi. So splitting that into 10 subintervals of the same length is going to be a length of, or a step of, pi over 10. So our start point is going to be pi over 10 after pi over 2. So let's see, pi over 2 equals 5 pi over 10. So we're going to start at 6 pi over 10. Or you could write that 3 pi over 5, however you like. So our start is 6 pi over 10. Our end is 3 pi over 2. Our step is pi over 10. And then we paste and write that in. We get a right sum of a negative. This here. I think that that's right. That would make sense because thinking about our unit circle, right? We've got pi over 2 and 3 pi over 2. And our cosine all on this side, which is what we're evaluating this way, all of that cosine is negative. So everything under that curve is also going to be negative. So it makes sense that our right sum is a negative number. Yeah, I think that's all for that one. So I've just got 3 questions left. This first one, they want us to set up a definite integral for this function, bound by these numbers here. So again, we put that smaller number at the bottom of our integral, higher one at the top, put our function inside dx, and now we want to not actually solve it, but approximate using a left sum in the following partition. So let's see, I know I'm going to sketch it out again to help us. We've got 0, 1, and whatnot. We're going to come all the way over here, 3, 4, 5, 6. Obviously it's 0. It is at 1. Our cube root looks something like that. Maybe not exactly, but something along those lines, just to get a good picture of it. You want to use a left sum, so we're going to start here. and go like that. Okay, which means that it's going to be the distance of 1, and then it's going to be this height, and this height. So plug in cube root of 3 plus cube root of 4 plus cube root of 5, and we don't end up including that because it is a left sum. And whatever this is going to be our approximation. I'm going to go ahead and plug that into my calculator. So cube root of 3 plus cube root of 4 plus cube root of 5. And that looks something like this. Awesome. Next up, and we've got a question pretty much exactly like this, I think, on our next homework, so on homework 22. And I do go over one just like this in that problem, or in that problem set in that video. But we will do it here as well. So we're given this function of negative x on this bound. So if I sketch a negative x, like f of x equals negative x, it's going to look something like this, right? And we're looking at it from -1, or -6 to -1. So I'm going to include that, and I'll just go up there. And somewhere in between these two numbers is some number c. We want to find two values of c within this interval so that our lower sum equals 20. So I'm just going to draw c right here. It might not be right in the middle. It might be like really close or really close to the other one. It could be anywhere in there, but I'm just going to do this so I can get a good picture of it. So obviously using my lower sum, that's going to be, in this case, that's going to be a right sum because this is just linear. So I've got these points here. So first I know that this distance is, well, let's see. If say c was like -3, the distance between them would be 2. Yeah, okay. So it's going to be that -1 minus whatever c is that distance. And then this distance is whatever c minus -6 is, or c plus 6. I believe, right? Again, if c was -3 plus, yeah, distance of 3. Okay. So now, remember we've got, so we're finding the area of this rectangle, so it's one side length, which is -1 minus c, times this height here, which is plug in -1 to -x, that's just 1, and then plus the area of this rectangle here, so it's going to be c plus 6 times this height, which is a -c, right, because if I plug that in there. So then I get -1 minus c plus -c squared minus 6c. Combine like terms, that's a -c squared minus 7c minus 1. Okay, we'll factor out a negative there. So it's c squared plus 7c plus 1. I don't know that we can factor that out, so we might have to use the quadratic formula for this. Oh, and I forgot a step, and I think I keep forgetting this step. So we want to set this equal to 20, because whatever this sum is, it's going to be equal to 20. That's what we're looking for. So, and let's actually undo that little factoring bit there, because it just makes it a little bit more annoying right now. So now I'm going to subtract 20 from both sides, and now I get -c squared minus 7c minus 21 equals 0. Now if I solve that for its roots, I don't think that is factorable either. Yeah, because it would be, yeah, there's no factors of 21 that add up to 7. Okay, so we're going to use that quadratic formula. And remember I factored out this negative, so just keep that in mind. So this c value is going to equal -7 plus or minus 49 minus, ooh, did I pick a poor number for this? I definitely did. This doesn't exist. Let's pick something other than 20. I don't really gotta really gotta think about these problems better before I set them up. Let's pick something other than 20. Because I do want C values to exist here. Let's try let's try 7. Oh, we'll try 8. Let's say it equals 8. So it's going to be negative c squared minus 7c minus 9 equals 0. Still have to use that quadratic formula. That's okay. And remember, I'm going to factor out that negative. So I know that negative c is going to equal this. We've got that 49 minus 36 divided by 2. So that gets to be negative 7 plus or minus, well, 49 minus 36 is 13 for 2. Excuse me. And I know that this is negative, so I know that c is going to equal the negative version of this. This is 2 possibilities for c. And I'm just going to type that into my calculator. So I'm going to type in first the plus. So I'm going to get negative 7 plus square root of 13 divided by 2, and then times negative 1 because of this negative here. So one of my c values is this. And then we're going to do that negative 7 minus square root of 13 divided by 2 times negative 1, again, because this is negative here. And then my other c value is, c has to be negative. I don't know what happened with what I factored out there, but it has to be in this area here. So ignore that. And it's going to look something like this. So basically what we just found is we've got a c value right about here and a c value right about here somewhere. Okay. And then for our final question, it's just finding our original function given the derivative and another detail. So we want to take the antiderivative or the integral of this. And that's only tricky because we have to use some u substitution here. So I'm going to say that u equals, well, I see that the derivative of cosine is negative sine, and that's in there. So I'm going to use cosine for my u. du equals negative sine of x dx. So now I can change this into the integral of u du, because I just substituted a u for my cosine of x and my du for these bits. Now if I take this integral or take that antiderivative, that's going to be 1/2 u squared because of our product rule. Not our product rule, sorry, our power rule. I'm just undoing the power rule there. And then I just plug in back my cosine. So it's going to be 1/2 cosine squared of x plus c. So what we just found is that f of x equals this. But we also know that if I plug in a pi over 2, my function equals 4. So this, and cosine of pi over 2 is 0. 0 squared is 0. 0 times 1/2 is 0. So that gets to be 0 plus c equals 4, or just c equals 4. So our function is going to be 1/2 cosine squared of x plus 4. And that's it. Sorry for messing up the setup for problem 10. That was unfortunate. But I hope that all of this made sense, and I hope that this was helpful. Yeah. Thank you for watching.